Any questions about anything before we start? Questions? No questions. Yes. Soon. I was hoping to have them done today, but I just didn't do it. So, I mean, whatever.
How does it look so far? Like the distribution?
They're still in a nice stack on my dining room table, you know. I took them with me when I went to Massachusetts over the weekend thinking I was going to do them there, but all these things intervened, so, you know. Hopefully I'll have them for you tomorrow. It doesn't take long to grade these things. Probably take me like 2.5 hours to grade the whole pile. Nathan. The weather was nice. Yeah. I saw this really cool thing in Boston, actually. My sister and her daughter's friend and I went in, and there's this like public art thing going on around Fenway Park. And there was this one incredibly cool thing, performance art piece. Basically what they had was they had a bunch of percussionists with all kinds of different percussion striking type things like rubber mallets, drumsticks, whatever. And they were arrayed like around the back of, those of you who are baseball fans know what I mean when I say the green monster, which is the most famous wall in all of baseball, all the girders and support beams and everything, and they were arrayed on that. And then there was some sound engineers and light engineers, and they played these pieces that were actually composed by striking with these different percussion instruments the different pieces that made up the back of the green monster, and they went together really incredibly well, and it was spellbinding. I mean, I swear, it was incredible. So creative. I wonder if they must have it on video somewhere, but it was like, you know, if you've ever gone to the Yamatai concerts, Cornell, the Japanese drumming, or the Korean group, what's Shimta? Yeah, those are pretty spellbinding too. And these weren't quite as loud and thundering as those, but they were pretty amazing. Anyway, so that was my fun. I was so taken by that I just couldn't concentrate on grading prelims. Sorry. Anyway, any other questions? Okay, well, let's get back to it, what we were talking about last time. We started talking about the Fourier transform, the continuous time Fourier transform. And essentially what we had was the definitions and some existence criteria. And there are these two very important equations that go along with the Fourier transform. One of them I call the equation script f, and that gives the Fourier transform in terms of the signal. And the other one is what I call equation script f inverse, and that gives the signal in terms of the Fourier transform. And I'm going to write these up just so I can point at them for the rest of the class when needed. And remember that it's one of these can hold and the other may fail to hold depending on the signals, and we extended the definition to include deltas both in time and frequency. And I had the existence criteria were things like if x is an L1 signal, then this equation holds, and this is a continuous function of omega. If x is L2, then these two both hold in an L2 sense. All that. You don't have to worry about all those details, but they're all in the monograph. The point is, the Fourier transform is complicated. It's hard to get a really tight presentation of things like existence and what it means and all that. And so I'm trying to aim for a kind of a workable, rigorous enough approach to it for us. All right, so that's sort of where we were at with the Fourier transform. And the big overarching idea, which is yet to be justified, and today I'm hoping to get to that, is that the Fourier transform of a signal is supposed to give you a description of its frequency content in some sense. So x hat is supposed to describe the frequency content of x. Just like the Fourier series describes the frequency content of a periodic signal, the Fourier transform is supposed to describe the frequency content of a not necessarily periodic signal. So x hat is supposed to be a frequency domain description of x in the same way that the Fourier series was a frequency domain description of a periodic signal. And also, by the way, there's this piece of notation we write, so I'm going to leave it over here, this double arrow between x and x hat. Okay. So anyway, there's a whole litany of operational rules associated with Fourier transforms, and I'm going to go through 3 of them in class, and that's where we were at the very end of class last time. So 3 of many, and you can see the monograph for a listing of all the rest of these operational rules for Fourier transforms. And these make your life easier depending on what you're trying to do. The first one is the time shift rule. And how does that go? If you have a signal that has Fourier transform, so if you have a signal x and it has Fourier transform x hat, then for any time shift, say t1 in the reals, the signal y equals shift t1 of x has Fourier transform y hat with specification y hat of omega equals e to the minus j omega t1 x hat of omega for all omega. And when describing these operational rules, when stating them, I will often use a sort of casual notation. The following is what I mean by that. So sort of informally, we often write something like this, that x of t minus t1 has Fourier transform e to the minus j omega t1 x hat of omega. Really what we need to do is say the signal with specification x of t minus t1 for all t has Fourier transform something with specification this for all omega. But this is the kind of thing you see in a lookup table in a more elementary book on Fourier transforms. Okay, now this is really easy to prove. Like you can start with equation script f, you can start with equation script f inverse. Maybe the easiest way to do it is starting with equation script f inverse. So to see this, to see why the time shift rule works, you start with script f inverse for the pair x and x hat, and that means that you have x of t equals 1 over 2 pi integral of x hat of omega e to the positive j omega t d omega for all t. And then you plug in t minus t1 for t, and you get y of t, which is x of t minus t1, is just going to be 1 over 2 pi. What happens when I plug t minus t1 in for t? I get this. And if you look at this last term here and this first term here, the underlined terms amount to equation script f inverse for y. Whatever's in the big parentheses under the integral sign has to be y hat of omega. So the underlined terms are script f inverse for y hat pair. And thus, y hat of omega equals whatever's inside the parentheses here. Okay, this is really easy to prove these operational rules in general. You could have also done it starting with equation script f if you wanted to. In that case, you would plug in y into equation script f. It's going to be x of t minus t1, change variables in the integral, and you'll discover that what comes out is what has to come out. Okay. And last time I mentioned that, and you could probably guess because of the morphological similarity of these two equations relating f and Fourier transform in a signal, for every yin there's a yang kind of thing, going back and forth between those. And we have a frequency shift rule, and in the current draft of the monograph, I call this the modulation rule. And I thought about this for years. I've called it both the frequency shift rule and the modulation rule, depending on the situation. And last spring, when I was teaching 2200, I thought it through again, and I decided, I think I'm going to go back to calling this the frequency shift rule and call the convolution and frequency thing the modulation rule. So, what is the frequency shift rule? Current version of the monograph, it says modulation rule. That's going to change shortly. If x has Fourier transform x hat, then the signal y with specification y of t equals e to the j omega 0 t x of t for all t. And this is for any given omega 0. That signal has Fourier transform y hat. With specification y hat of omega equals x hat of omega minus omega 0 for all omega. So multiplying by e to the j omega 0 t for some fixed frequency omega 0 in the time domain corresponds with shifting by omega 0 in the frequency domain. And you can see, and let's write it in the casual way. So here's the informal way to write this. E to the j omega 0 t x of t goes with x hat of omega minus omega 0. Compare this with that thing up there, the informal way of writing the time shift rule. You could see that one is sort of like the mirror image of the other. Something similar happening over in the frequency domain to what happened over there in the time domain. Something similar happening in the time domain here to what happened over there in the frequency domain. And that comes up again and again and again, that whole pattern of duality, so to speak. And I'm not going to prove this one. You prove it the same way you prove the time shift rule. You could start with equation script f. You can start with equation script f inverse. And you can look in the monograph for that. So the proof is similar to the time shift rule. And finally, the third important operational rule that we're going to use again and again is Anybody care to hazard a guess which one of the rules I'm going to pick out to be this third one? Alex? No? Okay, I'll rattle off a bunch of rules and see if one bubbles up to the surface of your mind as being really important. Time shift rule, frequency shift rule, time scaling rule, Plancherel theorem, convolution rule, frequency convolution rule. Let's see, what else? Time derivative rule, frequency derivative rule. What do you think is going to... Good job. Convolution rule. Who said that loud over there? Yes, excellent. Okay. And you didn't even take 2200 from me, right?
No, I didn't.
No, you didn't. So that means that Dorshuk or Tong or Chen or whoever you took it from did a good job. Dorshuk? Yeah, he does a much more continuous time version of 2200 than the rest of us do. I think you'll learn more about continuous time in his version. But anyway, okay, so the next rule I want to talk about is the convolution rule. Goes like this. If you have two signals, x1 and x2, with respective Fourier transforms, x1 hat and x2 hat, and convolution y equals x1 convolved with x2 exists, then y has a Fourier transform and y hat equals x1 hat, x2 hat. In other words, informally, well, no, I don't even have to do informally. I could just write it out this way. If I take y equal x1 convolved with x2, that has Fourier transform y hat equals x1 hat times x2 hat. Convolution in time maps to simple functional multiplication in omega. And there's a sort of a meta theorem of signals and systems math. To every transform, there corresponds a convolution rule. Okay, and we will see this. This is a symptom of being a transform, is that you have a convolution rule in your history. Okay, and we'll see that again and again. For the proof of this, for at least for L1 signals, see the monograph. For L2 signals, when I rewrite this chapter, I'm going to insert a clever, quote unquote, clever little way of proving it for L2 signals. But in any event, so for a proof, see the monograph. I don't want to go through it in class. But in any event, this convolution rule is going to be at the heart of why Fourier transforms are important to understand if we want to understand LTI systems. So we'll get to that as we go along. All right, so let me just do a couple examples of Fourier transforms. We've already seen like what happens with the delta in time, what happens with the delta in frequency, that kind of thing. So let's just do a couple of examples. Three to be exact. First one, this is one that comes up a lot when you're doing problems, and I just want to go through it just so you understand. So how about the signal x that has specification x of t equals e to the minus alpha t u of t for all t, and alpha is a positive number, positive real number. So this x is 0 for t less than 0, and then for t bigger than 0, it's just a decaying exponential. Signal comes up frequently in applications. Let's plug it into equation script f. And what happens? We get this, we get x hat of omega equals integral from minus infinity to infinity x of t, which is e to the minus alpha t u of t times e to the minus j omega t dt. And that's the same as the integral from 0 to infinity of e to the minus the quantity alpha plus j omega t dt. And when you integrate that, you get minus 1 over alpha plus j omega times e to the minus alpha plus j omega t evaluated from t equals 0 to t equals infinity. What happens when you evaluate at t equals infinity? If you have exponential of a complex number times t, and the complex number has a negative real part, then the evaluation at infinity is 0. And when you evaluate at t equals 0, that turns into a 1, and it cancels the minus sign. And this is what x hat of omega is for all omega. And the informal thing, the thing that you see in a table of Fourier transforms, is this. E to the minus alpha t times the unit step goes with 1 over alpha plus j omega. That's a typical table entry Fourier transforms. Does everyone understand that evaluation at t equals infinity? For some reason, people get confused about that, even at this level. Don't be shy if you don't. Tell me. Okay, good. All right. Nope, this is not the good kind of chalk. You can tell. Listen. Okay, listen to this versus this. See? The frequency content of... right? Okay, now here are two really, really important examples. Really important examples. Okay, how about PA? X equals PA. Remember what PA is? PA is a pulse of width A centered at 0 and with height 1. So unit pulse width A centered on t equals 0. Plug it into equation script f, and you get this. You get x hat of omega equals integral minus infinity to infinity x of t e to the minus j omega t dt. And in turn, that's equal to integral from minus a over 2 to a over 2 e to the minus j omega t dt. Let's do that integral out, see what happens. comes out to be a minus 1 over j omega times e to the minus j omega a over 2 minus e to the positive j omega a over 2. And the thing inside of the parentheses is minus 2j sine of omega a over 2 with a 2 in front of it. So this is what it comes out to be. 2 sine a over 2 omega divided by omega. So that's what x hat of omega is when x is this unit pulse of width a. What do we call a function like this? Sine something omega over something omega. A sinc function. So, i.e., x hat is a quote-unquote sinc function of omega with modulo some constants and whatever. Let's graph it, just to make sure we understand how to do that. First of all, why don't we have a problem at omega equals 0? We're dividing by 0, right? Yeah, L'Hopital's rule, whatever. Another way to remember it is sine theta over theta goes to 1 as theta goes to 0. Okay, so there's no problem at a equals 0 because sine theta over theta goes to 1 as theta goes to 0 by L'Hopital. And just in case you didn't know this, whenever you see a French word where there's a circumflex over an O, that means that back in the day there was probably an S after that O. So L'Hopital is like hospital, l'hospital, whatever. Anyway. Let's graph x hat of omega versus omega. And by the way, this is one of the rare occasions when the Fourier transform is actually a real valued signal. It has no j part, no imaginary part. What does this guy look like? You can verify that this is what it looks like. Let's see if I can do this. And the reason its amplitude is decaying as omega goes to plus and minus infinity is because the sine term is always between plus and minus 1. And yes, Amanda.
Is it when a equals 0 or omega equals 0?
Absolutely, you're right. Omega equals 0. Thank you. There is a problem when a equals 0. Well, actually, there's a problem with even considering it when a equals 0 because, you know, p0 of t is a really boring signal. Okay, thank you. Anyway, this is x hat of omega versus omega. The reason the amplitude goes down as omega goes to plus and minus infinity is because the sign stays between plus and minus 1, and the 1 over omega factor makes the decay like 1 over omega. What are the zero crossings? What's this first one here? What do you think it is? Okay, what is, all right, pi over a? Let's see. If I plug in pi over a for omega, I get sine of pi over 2.
Oh, wait, sorry. I was thinking of cosine.
Yeah.
Hey.
2 pi over a. Yeah, this is 2 pi over a. And this is going to be 4 pi over a. 6 pi over a. All the zero crossings are values of omega that make the argument of sine be an integer multiple of pi. And they're symmetric. And finally, what is the value at omega equals 0? Okay, the best way to figure this out, you could actually grind out L'Hopital, or you could turn it into sine theta over theta form. So I put a 2 down with the denominator, and I have omega over 2, and omega over 2, and then an a down with the denominator, and I have to put an a to cancel it. And that comes out, the value at 0 is a. Okay, the reason the value at 0 is a is the following. X hat of 0 is equal to the limit, as omega goes to 0, of sine omega a over 2 divided by omega a over 2 times a. See what I did there? And that's a times limit as theta goes to 0, sine theta over theta, it's just a. You have to get the argument of sine and whatever's in the denominator to be the same to use sine theta over theta going to 1. But you could do like Nathan likes to do and use L'Hopital if you want. No, he doesn't? What's that?
It's easier to write out.
Yeah, okay. All right, so there's a great example. This comes up time and again. And remember, we need a yang to go with this yin. Is this a controversial example, folks over there? These folks seem to be concerned about this. Is this a controversial example? Dan? You're arguing about fantasy football?
No, we're not.
Not this time. Okay. Only during the long, boring 75-minute classes, right? Yeah. Not the short, boring.
I think you mean the long, exciting 75.
Yeah. Is 30-30 a 75 or 50?
Well, 50, 7:40 a.m. discussion.
Okay.
Yeah, it feels like a 75.
So what's the yang to go with this yin? So this is sort of the flip side of this. Okay, item 2. That's going to be where we have a pulse-like thing in the frequency domain. So x hat of omega is going to equal 1 when, and I don't know how to, whatever, I'll just say minus omega m less than or equal to omega less than or equal to positive omega m and 0 otherwise. So this is what x hat of omega looks like versus omega. It looks like a flat thing of height 1 that goes out to plus and minus omega m. Then what is going to be the signal that goes with that? And you can predict what it's going to be, kind of, up to a few constants because of this whole duality issue. If I have a pulse in time goes with a sync in omega, what do you think is going to go with a pulse in omega? A sync in time, right. Okay. So plug that into equation script F inverse, and this is what you get. One over 2 pi, integral from minus omega m to omega m of just plain e to the j omega t d omega. And that's the same as 1 over 2 pi jt times e to the j omega mt minus e to the minus j omega mt equals, and in the parentheses I have 2j sine omega mt, and the 2j's cancel, and I get sine omega mt over pi t for all t. So a sync in time is the signal that goes with a pulsy kind of thing in frequency. And then we can graph x of t versus t. And what do we find? We find that it looks just like the x hat of omega look like versus omega, except we're going to have different things for the zero crossings. The zero crossings are going to be pi over omega m, 2 pi over omega m, and so on. Just whatever makes the argument of sine be an integer multiple of pi. And what's the value at omega equals 0? Let's see. What's it going to be? Well, it turns out to be omega m over pi, I think. Yeah. All right, so sync in time goes with a pulse in frequency. Pulse in time goes with sync in frequency. You get the rhythm, goes back and forth, back and forth. And before I talk about some of the kind of general rules of thumb about Fourier transforms, like, for example, what does it mean to be band-limited signal? What is it, when can you have something that's concentrated in time versus concentrated in frequency? Can something be finite duration and band, all that kind of stuff? I want to use the frequency shift rule along with example 2 to analyze the finite duration A440. Okay, so remember, recall, the finite duration A440 we want that signal to have frequency content around omega equals 2 pi times 440. Okay, we want there to be something 440 hertz-ish about a finite duration A440. Finite duration signals don't have Fourier series because they're not periodic, but they do have Fourier transforms. Let's figure out the Fourier transform of a finite duration A440. And there's plenty of finite duration A440s around. But there's a particularly simple one. So an especially simple finite duration A440 is the signal y of t equals cosine times 2 pi 440 t, all that multiplied by a pulse of width a centered at t equals 0. That signal is just an A440, so cosine 2 pi times 440t, when t is between plus and minus a over 2 and 0 otherwise. So it turns on at time minus a over 2, turns off at time a over 2. That's a perfectly good finite duration A440. And a general finite duration A440 would be instead of just having a simple cosine here, would have a whole Fourier series. But whatever. All right. Notice that you can write y in the following way. Y of t is equal to PA of t times 1/2 e to the j 2 pi 440t plus 1/2 e to the minus j 2 pi 440t. Cosine is 1/2 e to the positive j theta plus 1/2 e to the minus j theta, if cosine of theta. By example 2, conveniently still on the board, about to be erased, The answer is still up there. Example 2. PA of t goes with that sine of whatever it was, sine a over 2, 2 sine a over 2 omega over omega. By the frequency shift rule, PA of t e to the positive j 2 pi times 440t goes with, and let's just put a 1/2 in front of it just so we don't have to worry about that later on. So that's one of the terms over there. That goes to this evaluated at omega minus 2 pi 440. And the 2's cancel. And that's what I'm left with. And you can do the same thing for the other term, the one that has e to the minus j 2 pi 440. So 1/2 PA of t e to the minus, and by the way, I'm writing these informally in the informal way. You know, something of t goes with something of omega. And it's going to be the same as that, except with a plus in front of the shifting thing. So what happens here is that y goes with the sum of those two things. So y hat is going to be the sum of two sinks in frequency, one centered at 2 pi 440 and one centered at minus 2 pi 440. And graphically, this is what it looks like. If this is 2 pi 440, and this is minus 2 pi 440, what I have is, I have, roughly speaking, and the sinks overlap for all omega, so these are not exactly what this picture is dictating, but it's going to be something here. It dies out as you go over here, and then something here that dies out as you go over here. But the main thing to notice is that there's a blip around 2 pi 440, and let's recall what these values are. The first zero crossing away from that is going to be that plus 2 pi over a. So it's going to be 2 pi times 440 plus 2 pi over a. This one is going to be 2 pi times 440 minus 2 pi over a. And they're all going to be separated by 2 pi over a. And the height here is going to equal a half of whatever that was. So omega m over 2 pi, or where? I guess it's gone now, right? It was, I can figure it, I have to figure it out from scratch, sorry. It's going to be a over 2. A over 2. So the height here is going to be a over 2. And same thing over here. All right, now, why is this cool? This is cool because what? We want the Fourier transform to reflect the signal's frequency content. Even when the signal a priori doesn't appear to have frequency content, there's no reason for you to think of it that way. Certainly, if a signal a priori does seem to have frequency content, if there's a reason to think it has frequency content, like the finite duration A440, then we want the Fourier transform to reflect that. It does. See, y hat of omega is focused, concentrated most heavily right around the place where we intuitively think of y of t as having frequency content. And this provides at least the first piece of justification for thinking that the Fourier transform reflects a signal's frequency content. So to summarize this, and while I'm writing this down, think about that picture. Think about what happens when A gets bigger and bigger and bigger. So thus, y hat of omega is big around omega equals plus or minus 2 pi times 440. And what that does is it reflects our intuition that y has frequency content around 440 hertz, and y hat reflects the frequency content of y. Okay? What happens as a goes to infinity? As a goes to infinity, if you look at that picture, the height of that central lobe increases. The zero crossings get closer and closer together because they're always separated by 2 pi over a, and they squash in on 2 pi times 440, and the same thing happens in the negative frequency zone. So essentially what happens is as a goes to infinity, the picture for y hat of omega crushes in onto pi delta of omega minus 2 pi times 440 plus pi delta of omega plus 2 pi times 440. That is the Fourier transform of cosine 2 pi 440 t, which is what y of t becomes when a goes to infinity. So let me just draw a little schematic and then we'll quit for the day. So y of t equals cosine 2 pi 440t times pa of t. That goes with y hat of omega. And as a goes to infinity, this becomes cosine 2 pi times 440t, which has Fourier transform pi delta of omega minus 2 pi 440 plus pi delta of omega plus 2 pi 440. And y hat of omega converges to that. Okay, so I owe you a minute next time. Try to remember that. And again, I'll try to get your prelims back to you tomorrow.